Momentum chapter. The midterm exam is available from on Thursday to give you guys time, this time chunk to work it. If you can set that time chunk aside, that's where we'll be. I am probably going to be on campus until about 2 o'clock to stay till 4 on Thursday, which is really, really nice, and I like that idea. And I'm gonna probably get out of here so I can get some my house, trying to get reconstruction at my house has been entertaining. So, and then the exam is due on June 1st at midnight. So we know that Blackboard is supposed to be down from like 5 a.m. to 5 p.m. on Friday. If you can figure out how to access Mastering Engineering without going through Blackboard, go for it. But if you're accessing it through Blackboard, I've made an accommodation for that.
Wait, so Blackboard will be shut down the day we do the exam?
May 31st.
Which is
Friday.
Okay, so Friday will be down.
Yeah, if you're doing it on Thursday, you don't have to worry about it, but I was gonna give you guys 24 hours, but Blackboard was gonna be shut down for 12 of that 24 hours.
Okay, well, here's a question. WebAssign's a normal website, right?
Yeah, so is Mastering Engineering. You can access Mastering Engineering through Pearson Mastering Engineering.
Okay, so
I just am not, just that we're all set up to go directly from Blackboard into Mastering, but you can go to Mastering Engineering from outside like you can WebAssign.
okay, well, I have statistics homework that's due on Friday, I believe, and so and I'll probably do it Thursday, so that actually may not be a problem.
Yeah.
But if you do it, you go onto WebAssign, and what do you type in? I think I've only done it like.
I don't know. I don't remember. I have it as a link. Yeah, I have a link.
Okay.
Yeah, but so if you want to access Mastering outside of Blackboard, great. But I'm making accommodation for everybody that who typically accesses it through. So you have until, and make the assumption that once you open it up, that's your time slot, and I've got it set for plenty of time. And it's over 2 hours. It's over 200 minutes. I think I've got it set for. So you guys have plenty of time for that. The other thing that I've done for you folks is chapter 14 homework is all the adaptive follow-ups are due Thursday and Friday, but your homework for chapter 13 and chapter 14 are due. One's due today and one's due tomorrow. Because today's the 28th. So you got chapter 14 is due tomorrow. And then the quiz is due tomorrow for chapter 14. But that means what I also did is chapter 15, I don't have it due until next week. Even though we're starting chapter 15 right now. And I did get all the video posted. It was Friday morning before I did it, but I did get the video posted for last Thursday's class. So it's in Blackboard. So that kind of puts where we are, where things are rolling. And so we're going to start chapter. So I got to switch this button. Morgan, can you see the document? Is it positioned okay for you guys to see it?
Yeah, that was good.
Okay, good. All right. So chapter 15 is on impulse and momentum. And for those of you who took, there we go. And for those of you who took engineering physics with me, will have seen some of this derivation before, but now we're going to expand on it just a little bit. I always like starting when we do this, is we start with good old Newton's second law. And everybody remembers this as good old Newton's second law, but it's really not, right? We've already said that this is just the usual form, and it's the form that we're most familiar with. It's the form that we use most often, but it's not necessarily the form that gets us what we really want to look at. And one of the things that we talk about when we're dealing with this piece is we know that Newton's universal law is this one. And we went back and said that GME over the R squared of the Earth ends up being our acceleration due to gravity, which is another, it's again, we end up with another simplified version. But really what Newton said, and really if you go back to what he is doing, is that the sum of the forces wasn't related to this as much as it was related to a change P, and even our book uses the letter P, but we deal with what we call as a change in momentum. Right? This is my change in momentum. And if we look at this and we really write it out, we end up with a change with respect to time. And I'm going to actually do it this way, all right? We're going to actually start this way, even though we're going to use the simplified form here in just a second, particularly for the particle model and the rigid body model, all right? So remember, in our dynamics class, we said we were going to start looking at things as particles, and then we're going to start looking at things as rigid bodies. But we know that this is the most general form, and if I really look at this, I get a change in momentum with respect to time, and I write it that way, and that's my most general form, which means that I can rewrite this as the sum of the integral of a force with respect to time is equal to my change in momentum, right? So I can actually write it like this. This we define as impulse. And impulse is important because how I deal with my impulse also deals with what happens to my system. And the classic example, and if I'm not doing it ITV or I'm not doing it by video, the classic example is if I apply a force and I apply it slowly over time, this is going to slide with it, right? I'm not going to exceed it or anything like that, but if I give it a nice sharp pull, I'm not going to get that piece. Or in the classic example is the example of the video I always put is the fine crockery, right? They have the jars on there. And if I really get it, let's see if I can get it going really good here. If I really get it, oops, I hit the edge of the table. I can do it without actually moving the object, right? And it's all related to the change in time that I'm actually working with. So that impulse becomes important. So we could actually look at a couple of different things. So let's stick with this for a second so that I can have my forces, this is the sum of my forces, is now a derivative of momentum with respect to time. I can actually, you apply my chain rule, dt plus v dm dt. And when I deal with a rigid body or a particle, so if I'm dealing with a particle or a rigid body, okay, we'll spell it out again. I can't seem to write today. A rigid body, one of the things that we know is this change in mass term generally goes to zero. Particularly if I'm in a particle in a rigid body. Yeah.
Wait, you said change in mass. Why is the mass v in the end is something else?
This is a derivative. This is chain rule,
Okay.
right? So I can pull the m out and do the derivative with respect to velocity.
Okay, so you're doing the derivative with respect to mass, and that goes to zero.
This term goes to zero because there's no, if I'm dealing with a particle or a rigid body, I'm not changing mass.
Okay, all right.
The wheel's going to weigh the same, or the wheel's going to have the same mass once at the beginning and the end. But we know that this is not always the case. Right? This is not always the case. However, in this chapter, and in the models that we're using, when I have a particle or a rigid body, it is the case. Or it's pretty darn near the case. So let's kind of think through this. So if I have my pick-em-up truck, okay, so here's my, And we'll use the lovely farm pick-em-up trucks right now because our farm pick-em-up trucks are doing pretty decent. We're talking something on the order of 3,000 megagrams, right? I'm talking some 3,000 megagrams, or I'm talking, let's do it in pounds. Let's make this 6,500 pounds. I'm not, if anything, right now, if I'm changing mass, I'm adding mass, right? Because right now we're adding mud and everything else that we're ending up on the truck. So if anything right now that could be gaining mass because I'm adding more mud to the tires, more mud to the wheel wells, more mud to everything else. But usually what happens is I have a gas tank here and I'm using the fuel in order to get my truck to go away. But if I'm looking at my fuel, let's say it has a 40-gallon capacity and it's about 6.5 pounds per gallon for diesel. Or for gasoline, something around that. And I did not bring my calculator. This number, this gasoline number, is less than or much less than the 6,500 pounds. So over the course of any motion that I'm dealing with, I'm using a fraction of gasoline. This value or this change in mass associated with the gasoline consumption is really small compared to this, so I can still make this assumption for most of my cases that I'm not dealing with a change in mass. Right now with the mud, I may not be so, if I'm going through my pasture and I'm collecting mud on my tires, and if I've got mudder tires, it's not necessarily an assumption that I can make. But for the purposes of the problems that we're about to work in the homework, it certainly is okay, and we're going to make this assumption that I'm not getting a change in mass. So even the more general form that our chapter starts dealing with isn't the complete general form. This is the complete general form, and I do have to worry about that if I am dealing with rockets, where the mass is predominantly the fuel, and as that fuel gets consumed, I'm actually seeing a big, huge change in that mass with respect to time. I can't totally disregard it. So I have to worry about that term, but for right now, we're going to say that term goes to 0. And so I can end up with my sum of my forces is now equal to whatever my mass is, my change in velocity with respect to time. And remember, these are vector quantities. And so when we deal with one momentum, it's a vector quantity. So we're back to dealing with vector quantities again. So now I can also go ahead and do this. And we can go ahead and integrate this. And we can actually say, and this gives us our change in momentum theorem, that I can, if I'm doing this from V1 to V2, this is going to be mv2 minus mv1 is going to equal this right here. And now I have that this impulse equals a change in momentum. And we've seen this kind of before. Now, in physics, when we did engineering physics and we're back in that engineering mechanics, we started with momentum and then came back and showed that impulse was equal to a change in momentum. We kind of did it a little backwards. In dynamics, we're going to start with this piece and then use the momentum. Remember also, I have conservation of momentum. And that's where my momentum before has to equal my momentum after. And this applies for linear momentum as well as angular momentum. So I end up with both these momentums. The momentum before has to equal momentum after. My impulse is a change in momentum, and I have angular and linear momentum. We also have to remember a couple other things that we have to kind of worry about. We always will have total energy conservation. And we will have total energy conservation. The question is, where does it go? Right? Because remember, if I'm like in thermodynamics, right? If I'm in thermodynamics and I have a reaction here, I can have heat leave the system, or I can have heat come into the system. And the trick is accounting for where those changes are, right? And we know that if I'm got a block and I'm sliding it from here to here, and it starts with a 3 meters per second velocity, and now it has a 0 meters per second velocity, we've had a change in kinetic energy, which gave us work. Right? The change in kinetic energy gave us work. But we also have heat that leaves the system. So if I do the total energy on this side and the total energy on this side, I may see a difference due to a loss of heat here, because heat's not accounted for in my system. Total energy is always conserved, but I do have some, it's going to change, and the second law of thermodynamics says we can never break even, and because of that, my system may actually see a slight loss in energy, or it can see a big loss in energy. And we're actually going to work a problem here today that's going to show you, yeah, we got a loss of energy, and the question is, where does it go? Well, remember, there's lots of forms of energy. There's heat, light, sound. All of those are forms of energy, which pulls out of my system, and I can't necessarily use it for those pieces. And that kind of gets us to a point that we kind of glossed over in chapter 14, is I have conservative and non-conservative and we talk about this in terms of forces. I got conservative and non-conservative states of forces. So if I have no friction in the system, up down here at the bottom with kinetic energy and the total energy at the top, kinetic energy, but at that point the kinetic energy is 0 and the total energy, this would be something that we deal with in terms of conservative. But as soon as I add friction into the mix, I've got total energy at the top. Well, that's equal to the potential energy. I haven't started moving yet. That's all well and good. But the total energy at the bottom is going to be kinetic energy plus the energy that I've lost due to friction. So in real life, these aren't quite equal. Because now, in an ice rink, this number is so much lower. That energy loss of friction is so much lower than my kinetic energy. I can disregard it. And to 3 significant figures, I'm probably not seeing any loss of energy at all with a hockey puck on an ice rink. But if I'm on a gravel surface and I've got a box that's sliding down that gravel surface, that's not going to be, that's something I can't apply, and I do have to worry about those energy losses due to friction. And that comes into play when I'm dealing with different types of impacts, which we'll get into probably tomorrow. But we know that if I take my train here, and it's hitting the car, right? We've got this collision that's happening. Two things can happen. Well, lots of things can happen. The most practical of which is that this becomes boom, and I have pieces of the car flying everywhere, which makes it a little tough to work problems when you're trying to figure out what's going on with all those different pieces. But I got, things that are scattered everywhere. But we know that the train's going to slow down ever so slightly, right? Because we call this one an inelastic collision. We get deformation, we get explosions, we get a variety of different things, and we actually are going to see a loss in kinetic energy, okay? This one will have a loss of kinetic energy. Now there's a special collision that we usually see in terms of billiard balls, right? I got my billiard balls, they come in and hit and one goes off, and we call these an elastic collision. And if I have an elastic collision, I can have conservation of kinetic energy, but this is a special case. And again, as you guys go in your upper division engineering courses, you've got to understand when I can jump to a special case and when I can use that special case and how I can use that special case in order for things to make sense. So we've got a lot of different happen to apply to get us there. So, where we start to our, the FDT is now going to be my MV2 minus my MV1, and this is not how the book writes it. The book's going to write it like this. So this is my initial momentum, and I'm going to add an impulse, and I'm going to get a resulting momentum. Okay? But I'm still going to have conservation of momentum. I'm still going to have conservation of total energy. But now I'm looking at how the systems are going to interact and change with each other. I may or may not have conservation of kinetic energy. Depends on the special case that I'm dealing with. And these are vector quantities, so I'm going to have X components and Y components that I'm going to have to account for. Now, the fun part of writing these right here, like this, is we can do this. If I do a force per time plot, area under this plot becomes the impulse from T1 to T2, the force per time. So I can actually do plot and figure out what the impulse is as it extends over a certain period. And I can look at, this is still a force per unit time plot, and this is going to give me an impulse that looks like my force times my change in time. And this is when I have a constant force. That's when I have my constant force. So we can rewrite this in terms of an XYZ coordinate system. We can look at these force per unit time graphs that can help us out a lot. So if I'm reading automotive magazines, you'll see these kinds of curves. You'll see power curves. You'll see the kind. That's why a lot of the graphic information is a lot more helpful. And we're actually going to work a couple of problems that shows how you can use that back and forth. One of the other things that gives you is this. If I do a force per unit time graph, I can have a force per unit time graph with a constant force that looks like that. And I can have a force per unit time graph like this. But the areas of these curves, these areas, can be the same. So I have to kind of worry about my systems, and I can play with my coordinate systems. Okay? We can play with coordinate systems to help us out and keep us going, depending on how we're. Make sure my mouse is moving. we keep our mouse is moving. So we can take our area. So I've got a inclined plane and a box on the inclined plane. It's moving down with a force of 100 newtons, and this is going to be a net force. All right, and it's going down the plane, and I want to determine the impulse for t is equal to 2 seconds. Well, if I've got a system like this, I want to orient it along, so I'm just going to take my force, which is 100 newtons, and it's applied for 2 seconds. So this is going to give me 200 newton seconds. And you'll see this unit used a lot. And depending on how your mastering engineering wants the problems, you want to kind of look at that there. So I'm going to do something really. But that impulse is being applied at a 30-degree angle down the inclined plane. So I don't necessarily have to break it out into components for my particular system. So let's look at my Newton seconds. Okay, this is a kilogram meter second squared times seconds. It's going to give me my kilogram meter seconds. And this is our traditional momentum unit. But we can also see this is a momentum unit. So we can see both of those pieces that are there. Now, I'm going to do one of the fundamental or preliminary problems because I disagree with the book, and I will show you why I disagree with the book. So what we've been given is a box, and we're applying a force. And it's given that that's 30 degrees. But instead of giving us a value for the force, they give us a graph. Okay, they give us a graph, and this is a force per unit time graph. It's a, I'm going to do this. This is 20 newtons, okay? That's 20 newtons. We're given, this is 1 second, and we're given that this is 3 seconds. The force is going to be applied until we get to 20 newtons, and then a constant force is applied to 3 seconds. And we want to find, and the problem states they want to know the impact for the first 2 seconds. So the impulse for the first 2 seconds. Well, we just saw that my impulse can be looked at as the area under the curve. So, all right, So for the first second, I've got 1/2 20 times my 1 second. Okay? That's my area under that curve. And then for the next second, because I'm going to go to 2 seconds, I'm going to have my 20 times my 1 second, and that's going to give me, this is going to give me 10, and this gives me 20, and this ends up giving me 30 Newton seconds. If you look in the back of the book, what they've done is this. They've done the 1/2 21 plus 20 times 2, and that's this time interval there. And so they end up with 10 plus 40 is equal to 50 Newton seconds.
Wait, so you said in the book they give
This
you
is the
graph?
answer that the book gives you.
Oh, okay.
What I think that's being done in the book is they gave you the total impulse for the graph given versus what the question specifically asked, which was for 2 seconds.
Oh, okay. But what I was going to ask you, said in the book they give you, so you disagree with that. You don't disagree with them giving you a graph.
No, I don't disagree with them giving me the graph at all. I disagree with if I'm looking for the total area under the graph, it's right there. If I'm looking for the impulse to 2 seconds, which is what the question is, what the book has done is they've given you 6 or 7 different representations and says, tell me what the impulse is at t is equal to 2 seconds.
Okay. I thought you were saying you were going to say you didn't like the graph.
No, I like the
Saying
graph's
you just-
fine.
oh,
Graph's
okay, so
fine.
I like that.
I'm disagreeing with the answer. Yeah.
Was it to find the impulse at t equals 2 seconds or within the whole 2 seconds?
Within the whole 2 seconds. Just like the first one that I did, this one, we're doing it for the 2 seconds down the inclined plane. This one, they give you the graph, and you go, okay, and then you go look it up in the answer in the back of the book, and they actually give you this equation, and I'm going, but that's for the whole 3 seconds, not for the 2 seconds. So just was showing you that that one I kind of picked out because I actually disagree, and I don't disagree with what they've done because that's the whole area under the curve. I just disagree that they've kind of done 2 different problems. All right, so let's do one. Which one do I want to do first? We'll do this one first. All right. So I have a 20-pound block. And it's going to slide down an inclined plane. And the plane has a 30-degree angle. There's a coefficient of friction. We knew we couldn't do things without friction for very long. It has an initial velocity of 2 feet per second. We want to know what is the velocity after 3 seconds. All right, it's a typical inclined plane problem, right? And now that I'm bringing in friction, I got to worry about that. So there's my 20 pounds. I'm going to have a normal force, and I'm going to have a force due to friction. So I got to worry about this. So I've got my force parallel is going to be my 20 sine of 30 degrees. My force perpendicular is 20 cosine 30 degrees. Now, I'm going to still work along my inclined plane. But I have to have this because this is my normal force. And this is the force down the plane. And I got to have my normal force because I got to have my force due to friction. Okay? So what I'm going to have is I'm going to have the mass times velocity plus force Alright, so there's my equation. But now I've got to worry about this force is due to the block, but I also have to do my force due to friction. Okay, I also have to do my force due to friction. So the force that I've got to put into here is going to equal my 20 sine of 30 degrees minus the 20 cosine of 30 degrees times my coefficient of friction, 0.25. And when I plug that into the calculator, you end up with 5.67 pounds. Of F dt is going to be 5.67 pounds times my change in time, which in this case is, so that's what I'm going to end up putting in here. So now I'm going to put in my variables. I've got 20. My initial velocity is 2 feet per second. And I'm going to add my 3 seconds is going to be my 20 divided by my 3.22 for my velocity. And when I saw 29.4 feet per second. Okay. All right. Now this one can be done, the one I'm about to do can be done a number of different ways. I'm going to show you how I did it, and then I'll show you how the book does it. And then I'll show you a couple of things that go along the way. So we're going to start. We've got a 400 kilogram object is being towed with the force described. We want to find the velocity at 8 seconds, and we want to find the... Okay, this is 600, this is 750, and this is force. This is 5 seconds and 8 seconds. So I'm going to get a nice graph here, and then I'm going to get this graph here. All right. So I want to find the area, and I can start with mv1 plus the sum of my lovely f dt is going to equal mv2. This is my impulse, and that equals the area under the curve. So I'm going to calculate the area under the curve. It's a nice curve. It's easy for me to do, so I'm going to do that. So I'm going to get 1/2 600 times 5 plus, oops, did I lose people? Is that a question? Did I get a question from somebody? Go back here. Okay. Oh, no, here's a message. Hang on. the exam is available Thursday. It's going to be available from whatever time it's set. It's like 1 a.m. until Saturday because Blackboard is going to be down. And I've got it set for like 210 minutes or something like that. So it's set for plenty of time to do it, but you want to sit down and make sure that you can do it all in one sitting. So, okay. All right, got it. I'm just making sure since somebody threw in a question, I wanted to make sure. Okay, so we've got that part. This is the area under that part of the curve, and that's 600 times 3. And then I've got the 1/2 150 times 3 for this part of the curve. And that's going to give me 3,525. Okay, from the area under the curve. My initial velocity was 0. So I got rid of that. So that makes this super simple. 3,525 divided by 400 is going to give me my velocity, final. Because there's my mass there, so that's where that comes from. And it gives me 8.81 meters per second. Okay, so you're going, all right, so that's pretty easy. Now I got to worry about distance traveled. And we're most likely to want to go and do our kinematics equations. Because we are used to that. We've done that, right? We most likely want to do that. And we have a graph, and you go, okay, I got my graph, right? And here's my force, here's my time. Force is equal to mass times acceleration. So if I do acceleration, there's force divided by mass. And I'm looking at my graph, and guess what? A is not constant. And that's a reminder that our kinematics equations are written when we have a constant acceleration. Our kinematics equations are not written when I have a variable acceleration. And this graph right there tells me I have a variable acceleration. So, that means bummer. I gotta figure out another way to do it, right? I gotta figure out another way to do it. So let's look at the long way to solve the problem. So, we've got two parts to the problem. We've got the part of the problem from t is equal to 0 to equal to 5 seconds. And if I look at my graph, I've got force, and that's 600. Where do I want to do it? Divided by 5t, and that's coming straight from the graph. There's my 600, there's my 5. I'm doing the 600 divided by 5 to get my slope. That's just coming straight from the graph, and that gives me 120t. Now I do my 120t dt is equal to my mass times my velocity, which is equal to 400v. Do the integration, I get t divided by 2, 120, is equal to 400v. And I end up with 60 divided by 400 t squared is equal to v, 15t squared. And my velocity at this point at 5 seconds is equal to 3.75 meters per second. So I can find that lovely. For t is equal to between 5 and 8 seconds, I get my divided by time minus 5 is equal to 750 minus 600 divided by 3 time. That again is coming straight off the graph.
So 750 minus 600 divided by what? Can you,
3,
oh, by 3.
yeah, because it's between 5 and 8. So it's 8 minus 5,
That equals 50.
okay?
Oh,
Alright, so I clean this up and I get the force is equal to 50T plus 350. So now what I get is I get mv1 plus my force dt is equal to mv2. So this is 400, 3.75, which we got from the first calculation. Divided by 400, you'll see why. And now I've got my 50 is equal to velocity 2. So I took this mass, divided it through all of this. So now I've got V2 is equal to 3.75 plus 1 over 400. And now I get the 50t squared divided by 2 plus 350t evaluated from 5 to t. And if you do the steps, you get 375, and you end up with 0.0625 t squared plus 0.875 t minus 0.0625 times 5 squared minus 0.875 times 5. And when that's all cleaned up, you get 0.0625 t squared plus 0.875 t minus 2.185. And when you plug in for 8 seconds, this gives you V is equal, or meters per second. So I end up in the same place, just took me a little longer. But this part's going to help me at the next part because I've got the integral of ds is equal to the integral of v dt. And I have to use this because a was not a constant. So I do this at 5 seconds, or t is equal to 5. And so I plug in for this v, it's my 0.15, or my 0.15 t squared dt. This right here. And this gives me 0.15 t cubed divided by 3. And if I'm evaluating it at 5, this gives me 6.25 meters. So in the first 5 seconds, it travels 6.25 meters.
And that was at t equals 5 seconds.
That's t equals 5 seconds, but I got to know the distance at 8 seconds. So now we get ds is equal to v dt again, except now I'm going from 5 to 8 seconds, except now I've got this not real pretty, but not impossible. And so this gives me 0.0625 t cubed divided by 3 plus 0.875 t squared divided by 2 minus 2.187 t, and that's evaluated from 5 to 8. And when you do that and plug in the numbers, you get 18.56. So the total distance is going to be my 6.25 meters plus my 18.56 meters, which is going to give me my 24.81 meters. Everybody good? All right, let's do a kick of a ball. So this time I've got a ball that's kicked, and it's going to go off at 60 degrees. And it's going to end up on a horizontal surface, and it's going to end up 12 meters down the way. The ball has a mass of 0.15 kilograms. And we want to determine the impulse. We're going to have to use projectile motion. So Vx is going to equal my velocity cosine of 60. Vy is going to equal velocity sine of 60. Acceleration in the x is equal to 0. Acceleration in the y is equal to 9.81 meters per second downward. And we can use, in this case, we can use my change in distance is going to equal v naught y times time minus 1/2 gravity times time squared. My change in distance downfield is we started here, we ended up here, so that's going to equal 0. So that's going to make my life a lot easier. Vyt minus 1/2 g vy minus 1/2 gt has got to equal 0. That's v sine 60 degrees minus 9.81 divided by 2t has got to equal 0. I want to solve for t, so t is going to be v sine 60 to 9.81. I'm going to use my x equation because I know my change in distance is equal to vx times time plus 1/2 at squared, but there's no acceleration in the a direction. So I get 12 meters is equal to v cosine 60t, which is v cosine 60 sine 60 9.81 2v, because all I did was plug that in for t. You can play with that, and that gives you v squared is equal to 136, which gives you v is equal to 11.66. The impulse is going to be the mass times velocity, and that's going to be my 0.15 kilograms, 11.66 meters per second, and it ends up being 1.75 Newton seconds. Now I can use these, my kinematics equations, because once the impulse has been applied, I do have a constant acceleration. I'm not applying a new acceleration in the x direction, and the only acceleration is in the y direction, and that's a constant acceleration due to gravity. Okay. Let's have a fun one. So I have a vehicle. It has a mass of 2,500 kilograms. It has an initial velocity of 27.78 meters per second. It has a final velocity of 11.11 meters per second. What happens is this vehicle is going to, the person in the vehicle is going to stomp on the brakes, and we're going to get a skid. And the skid is going to last for 5 seconds, and this is the change in the velocities in that 5 seconds. We want to find the coefficient of friction. Okay? We want to find the coefficient of friction. So I'm going to do a little rearranging. I'm going to say that the impulse is equal to a change in momentum, which is going to be my 2,500. My final is 11.11 meters per second minus my initial, which is 2,500, times my 27.78 seconds. And that equals to be a negative 41,675. And this is in kilograms meters per second. But that impulse is going to be the force that's being applied times my change in time. But the force that's being applied in this case during the skid is this right here. It's just friction is fun. So now I get mu normal time is going to end up so even though this is negative, I'm going to get the coefficient of friction, which is just my ratio. And my normal force, which is going to be mass times the other, is going to be so if I do my normal, this is mg, right? And that's going to be minus 24,525. Normal force is reverse of that, or the normal force. So I'm going to get my 675, 24,525 times my time, which was 5 seconds. It's going to give me a coefficient of 0.340. And the last one for the day stuff and start looking at energy. I've got a 10 kilogram package. Is going to come out of a chute. It's going to hit a cart, and the cart is a 25 kilogram cart. And it comes out of the chute at 3 meters per second. And the cart is going to roll freely once it hits. And we get to disregard friction at this point. We want to determine the final velocity, the impact, and an energy ratio. And it's an energy loss ratio. Okay. So basically what we have is this, is we have the boxes coming out of the cart and in the chute, and that's a 30-degree angle. Write it bigger so people can see it. It's a 30-degree angle. And we know what happens. The box is going to hit the cart, and the cart's going to roll that direction. So first I'm going to use conservation momentum. And so I'm going to have the mass of the package, the velocity of the package, cosine 30 degrees, because this is my x direction. My momentum of the cart to start is 0. The package and the cart are going to be together at the end, so this is the mass of the package plus the mass of the cart. And this is the velocity in the x direction at the end. So this is 10, this is 3 cosine 30 degrees divided by 10 plus 25 is going to give me the velocity in the x direction after. And that works out to be 0.742. Now, this is confined to work in that direction, so the velocity of the y direction has got to equal 0. Because we have no component in the y, just from the description of the problem. So now I can use my mv plus impulse is equal to, this is mv1 plus impulse is mv2. I can use that to help me find my impulse. And my impulse is going to be a vector quantity. So if I'm in the y direction, okay, I'm in the y direction, this is a minus from right there. So I, for that, is just going to be my 10 times my 3 times the sine of 30 degrees equals 15 Newton seconds. And so that's in the y direction. Now the x direction, I'm going to have m1v plus my impulse, except now this is MP velocity of the package after. And this is velocity of the package. This is going to be MP VP cosine of the angle plus I is equal to MP velocity of the package after. I works out to be 10, and this is the 0.742, that's this term, minus 10, 3 cosine 30 degrees. This ends up giving me a negative 18.7 or 18.56 Newton seconds. So now I is going to equal the square root of 15 squared plus negative 18.56 squared. And that works out to be 23.9. And then I can do the tangent of my angle. Y is 15, x is minus 18.56. And the angle is approximately 38 degrees. Now I can calculate the energy. So I'm going to use kinetic energy 1/2 mv squared. And my initial energy is 1/2 10 times the package, 3 squared is going to be 45 joules. T2 is now 1/2 the combined. I think it's the combined. It should be 35. And that's 9.63 joules. And the ratio that they're talking about is this one right here. And I get my 45 minus my 9.63 divided by my 45 ends up being 0.786.
So is the bottom energy total energy, or is it just T1?
It's T1, because you're doing the before and after. You're doing the loss ratio. This is the energy lost ratio to the beginning, so it's the energy lost ratio. And from a physical property point of view, I'm losing energy due to heat into one place. Okay, I'm losing it because we know, but from experience, what happens here, right? If it's coming out of the chute and it hits something, I'm going to get a collision. I'm going to get some heat generated from the collision. You know, I not a whole lot, but I am. I also get that sound when it hits, right? But most of that energy lost is the fact that I can't move the earth. You know, the earth is
Stationary.
in this case stationary. There is a reaction back, but it's like that rebound effect, and so I'm losing energy into the earth from that perspective. It can go into deformation, you know, it can go into a variety of different places, but because I'm losing this Y component, because I'm constrained to go this direction, I'm losing that Y component, I'm losing the energy there. It's work that I can't get back out. Mother Nature says we can't get it for nothing. All right, so we started conservation of energy. We'll start working more on conservation of energy. We'll start looking at angular stuff. We will not meet on Thursday. You can use this time to take your test. You guys good? And I should get this posted this afternoon.